Okay, so the plan for today is to finish another problem or two in 5.1. So we talked about discrete probability distributions, finding expected values and standard deviations last time. So just going through another couple problems. That's, a somewhat involved process. So just hitting that topic once more. We'll talk about some proofs of some previous theorems, just some kind of background knowledge. This is a math course, so when I make a statement, when I claim that something is factually correct, either a theorem or whatever, I, I try to provide ideally a formal proof of that, but that's usually not really possible in statistics. Usually the mathematics that we would need to prove these things super carefully is a bit beyond what's expected from the prerequisite material for the course. But I either try to give some empirical evidence, so maybe some simulations or something that makes such an argument, some logical reasoning, some reason that, for instance, we might want to choose the median over the mean if we want to convey some certain thing, or how do the measures of center, how are the measures of center affected by outliers or skewedness, for instance. Um, or in this case, we will actually work through a couple of actual proofs. So this will give a little bit of a flavor of kind of what, the actual formal proofs of some stats things look like. We'll prove a couple of important theorems. So Chebyshev's theorem, the law of large numbers, and we'll also uncover a few complexities that maybe will help you appreciate kind of the underlying structure below all of this statistics. So it's not just that we're picking, you know, um, approaches or models or ideas that kind of feel right or feel good or something like that. There is a lot more formality that's under the hood that we're just not looking at at this level of coursework, but at a higher level of coursework, there's a lot more depth to all that we're discussing. And then lastly for today, I'm not sure how far we'll get into this or whether we even get to it, but we'll plan to at least start binomial distribution 5.2 and the Poisson distribution will be, I'll leave that to a supplemental video, and I might also punt binomial distribution to a supplemental video as well. Um, so after today's class, I'll see, how far we got, what we're going to put into a supplement, and then I'll post the video. I'll post the link on Blackboard and I'll add the video to our YouTube playlist so you can, watch that. That'll be kind of the rest of the makeup for that day that we missed last week. So again, kind of flexible on how much will be in that supplement and how much we'll get through today, depending on how long these first two pieces take. Just another reminder, the Examity practice exam is available. Check the Blackboard announcement for more details on that. And make sure to watch that Harrisburg Area Community College video and to read through that the URL that I posted, the user guide on Examity's website. Make sure to go through those, preferably before trying to do the whole Examity thing. It can be a little bit complex the first time you do it. There are, a few steps that you have to get in kind of the correct order. And just a reminder, the Examity practice exam, which is hosted on my stat lab, it is password protected. The password will be put in by Examity. So it's not like you're not going to put in the password that you use to log in to my stat lab, or it's not like your personal password. It's a password specific to that exam that is hosted on Examity's website. Through the browser extension, Examity will add that password in when it's time, and then that gets you into the exam. And that just basically, that provides a link between the two systems from Examity to my stat lab. And that basically ensures that you don't accidentally start the actual exam without the Examity window being open or without Examity being, without the session being available. So I wanted to give a little more detail on that because I'd gotten a couple of emails with questions about that password and how it works. I think I probably also should post the Blackboard announcement just clarifying that as well. But okay, any questions on anything up to this point? uh, with either the exam stuff or the material. Okay. The quote of the day today is from chess grandmaster Daniel Darenditsky. I think we already had a quote from him. There's kind of two quotes of his that I like. One dealing with abstract versus concrete advantages, and this other one of his that I like. He's a chess, streamer and YouTuber and so on. And chess got really big over the pandemic. So um, what one of his quotes is, "Not all pieces need to be climbing Mount Everest all the time." Or kind of during COVID times, you would say, "Not all pieces need to be, delivering the COVID vaccine or flying the COVID vaccine across the country." Um, and I think this is, an important note is that, you know, burnout is easy, right? It's easy to throw yourself into something so hard and so thoroughly that you end up getting burned out before you even realize it. So, at this point in the semester, it's, about halfway through the semester, midterm exams and midterm projects are probably hitting around this time. You're getting midterm grades back, all these kind of things kind of happening at once. Um, do you need to be giving your absolute all in every course, all of the time? Maybe not. You might take a look at your coursework overall and you might say, well, in these two courses, I have like a 97% or something. I can give up a little bit of time in there to say boost my grade in a course where maybe I'm not doing as well as I want to, right? So you can maybe pull back a little bit in some areas, push forward in some other areas. Um, you don't need to be going 100% all the time in every course. I know that, faculty like to think that that our course that you're taking is the only course that you're taking and the only responsibility you have in your life, but we all know that that's not true. You're balancing coursework, you're balancing life demands as well. So make sure to balance that in a way that, doesn't burn you out, that is sustainable, and that you're able do well across a broad range of activities. Okay. So let's look at this example. I actually have also a similar exercise down here. So actually, I'm going to try to post this in the chat. We'll see how, I don't know if the math type stuff will post very nicely or not. We'll see. Oh, it looks like it actually posted as a picture. That's pretty cool. Okay. Well, it looks like it kind of posted in the chat. Um, so this is the exercise. It's going to be similar to the one that we're doing. So if you want a little bit of practice on this, because again, I know that it's, quite a few steps to get these answers. Here's a practice exercise along with the answers. So the setup is going to be the same. The 250,000 is the same, and the general idea is the same, but the annual premium for the policy being 350 will be different. This number will be different, this 0.998734. And then, of course, the answers will be different. $33.06 for the expected value and $8,902 for the standard deviation. So if you basically record those four numbers, those are the numbers that are different from the previous example to this one. Or of course, you can come back and look at the YouTube video and see this as well. Okay, so the example here is we have a $250,000 one-year term life insurance policy on a 20-year-old female. The annual premium for the policy is $200. So that's how much the person who owns the insurance, in a sense, the insured, the policy holder, that's how much they pay per year, the premium. And the probability of surviving the year for that person is 0.99954, right? 20-year-old females don't die very often, so pretty high probability of surviving that year. So you pay the $200 no matter what. And then if that person dies that year, their beneficiary or beneficiaries, receive the $250,000 payout. So what does this look like from the insurance company's standpoint? Oh, let's let X be the profit for the insurance company. Now we have a qualitative variable that's kind of determining the profit, right? Does the person survive the year or not? That's a qualitative variable. But we do notice that that gives rise to both the profit for the insurance company and it's linked to this probability number. So X, the profit for the insurance company, if the person survives the year, the insurance company takes in $200, doesn't have to pay anything out. That's plus 200. And, for those of you who are going into accounting or finance or something, you might balk at me calling this profit because, I mean, of course, the insurance company has other expenses. They need to pay employees, they need to keep the lights on, but we're talking just kind of locally here, just for this policy, is this policy profitable in the sense that does this policy pay out more than it costs us? So we would get $200 from the premium. We would have to pay out nothing to the insured as the insurance company if they survive the year. So we're plus 200 in that case. And that happens with probability. Well, what's the probability of them surviving the year? This number, 0.999544. On the other hand, if the person does not survive the year, we still get our $200. We still get plus 200, but then we have to pay out 250,000. So really we're at minus what, 249,800. And that happens with probability. Well, we don't have this probability, but I think it's pretty clear that the person either survives the year or does not survive the year, right? Those are complementary events. So I know that this probability is going to be 1 minus 0.999544, or that's 0.000456. If you want to do 1 minus a decimal number, you just make all of the decimals add up to 9, and then the last one add up to 10. And then that 10 kind of cascades over and, turns all the 9s into 10s. That 1 kind of jumps all the way over to the left. So 9 plus 0 is 9, 9 plus 0 is 9, 9 plus 0 is 9, 5 plus what is 9, 4, 4 plus what is 9, 5. And then for my last decimal, 4 plus what gives me 10, that's going to be 6. So this sum is 1. So this is a probability distribution. And because I don't really want to do all the calculations by hand, we have another example down here where we will go through it by hand. We're going to jump over to Excel, right? These are pretty nasty numbers. We're going to leverage Excel to help us with these calculations. So let me just pop this information over here into Excel. So I have 200 and negative 249,800. Don't put the comma in when you type it into Excel. That looks good. And then for the probabilities, I have 0.999544. Let me expand this just to make sure I type that in right. Looks good. And then for my second probability, 0.000456. Or since I'm using Excel, I could do equals 1 minus this probability. I could do that as well, and that would give me that same answer. So this is my probability distribution here. And then I'll do what I've done before. I'll kind of build off of this probability distribution. I'll append a couple of columns to compute my expected value and my standard deviation. So recall that my expected value is x1 times probability of x1 plus x2, probability of x2, and so on for all of my outcomes. So I need to take my outcomes multiplied by their associated probabilities and then add them together. So that's this next column over here. Maybe I'll even try to make it green. I think if I make it green, it might be hard for you to see. So I'm going to keep it black. But this is what we've kind of drawn in green over here. X times probability of X, we're appending this column This is the probability distribution. We're kind of just globbing this column onto the end to help us compute the expected value. So I'll take 200 times this 0.999544. So I see that's the product of those two cells that are to the left of the cell that I'm in now. And then I can, on the bottom right, double click and drag. And I see that everything kind of moves along by relative reference. So this next cell down is still looking at the two cells directly to the left of it, taking their product as we would expect. And then what's my expected value of X? Let's just right align that so it looks a little nicer. It's going to be the sum of this column, X1 times probability of X1 plus X2 times probability of X2. In this case, I'll just do plus because it's a little quicker than typing out sum because there's only two of them. So my insurance company's expected value is positive $86. They expect to make, on average, $86 from this policy. Now, keep in mind, they, from a business perspective, they still have to pay their employees, pay their underwriters, pay for all of their, computer servers and all of that stuff, all the fancy little apps and things that you can get your information on. They need to pay to keep their lights on and stuff. So that all comes out of here as well, right? So from a business perspective, this isn't purely profit, but from a stats perspective, we'll kind of cut off the concerns there, and we'll say on this policy they made $86 according to these numbers. We also want to compute our variance and standard deviation, so we append a couple more columns, and we remember that the variance of X, on one hand, this is the average squared deviation from the mean, or the expected value of X minus mu squared. But practically speaking, it's usually easier to compute this as expected value of X squared minus the square of the mean, minus the square of this number there. What is expected value of X squared? Well, it's clearly not expected value of X all squared, because then I would get the same thing minus itself, and I'd get 0 all the time. That's not a reasonable variance. This is X1 squared, probability of X1. The probability does not get squared, and so on. So I square each of the outcomes, multiply by their original probabilities, then add those together. Very similar process to computing expected value of X, but the outcomes get squared. So now I need to append a column for X squared. This is just going to be the outcome squared. This little caret symbol is the exponentiation symbol in Excel. It's, what is it, shift 6. So 200 squared is 40,000, and well, I guess we could just double click and drag, and we see 6 times 10 to the 10th for 249,800 squared. Right, this is why I didn't want to do this by hand, because we have big numbers. All right, we could have done this by hand, but it's just cumbersome keeping track of all these numbers. And now I want to take these X squareds times their probabilities. So I want this number multiplied by the original probability. And again, I'll just click and drag. And then I want the expected value of X squared. I'll put that apostrophe there because I don't want to actually say tell Excel to compute something here. I'm just noting that this number I'm going to get here is expected value of X squared. I don't want to write it over here because then it'll get jumbled up with all this stuff. And that's the sum of these two. So that's my expected value of X squared. My variance of x then is this number minus this number squared, expected value of x squared, minus the mean squared. Remember that the expected value of x, we often also call that mu. We actually note that it really doesn't change anything at all materially, right? We still have 2 times 10 to the 7th, 2 million minus 86 squared, that's maybe something like 10,000. 2 million minus 10,000, still like about 2 million. And our standard deviation, the square root of the variance, is about 5,300. So we see we have an expected value of $86. On average, we'll make $86 per similar policy. And our standard deviation is about 5,337. So if we had a whole bunch of policies and we got to average them together, if we had 1 million, 2 million similar policies, and we have a whole bunch of people in this pool that are paying in their $200 and not taking any out, and we have a couple folks who didn't survive the year that we have to pay a whole bunch of money out to them from this pool, the pool will be net positive on average by about $86 per policy. But on an individual policy basis, there's actually a huge risk here, right? I mean, this is clearly not close to a normal distribution, but if we were to just kind of look at that, mean plus or minus 2 standard deviations kind of idea as being kind of reasonable values, well, we're basically anywhere between minus $10,000 and plus $10,000. Or of course, we see that, this is actually a simple enough distribution. We could just look just directly at the outcomes. We either make a little bit of money almost all the time, or we lose a ton of money in a very rare case. It's actually kind of the opposite of like a Powerball, right? If you play the Powerball, like you lose, say, $1 most of the time, but you win a ton of money very, very rarely. This is kind of the opposite bet, right? The insurance company is taking in a small amount of money most of the time and paying out a huge amount of money on occasion. So it's actually really important that the insurance company gets these numbers right. If they pay out a huge amount of money, even a little bit more often than they expect, it can be really disastrous for them. It is an interesting question, though, when you look at, to earn $86 on, on a policy, a $200 policy, and subject yourself to this much downside risk, is it actually worth it? Why would it be worth it for the insurance company? And actually, when we get into chapter 6, we'll get maybe a little bit of a deeper insight into why an insurance company might be willing to do this. I mean, this looks crazy. Why would any company ever take on this kind of an investment where they stand to make less than $100, but their standard deviation is huge? And the reason is related to the central limit theorem, and what happens to the standard deviation whenever we pool together lots of independent risks. If the insurance company is able to bundle together 100,000, a million, 10 million policies from different policyholders, that actually makes a huge difference for them. And we'll look at that in chapter 6. Okay, again, if you want a little exercise working with these numbers in Excel, try your hand at this problem with, it's the same setup, just slightly different numbers. And here are the answers. All right. And of course, the male policy costs a little more because men tend to die a little more frequently when we're younger because we tend to do some stupider things when we're younger. So if any of you have seen, I don't know if the movie Jackass is in its like, 8th or 10th or 20th rendition now or whatever, but if you've ever seen that movie or that TV show, then, you see you see why us guys tend to pay a little more for life insurance, shall we say. Okay, any questions on this problem? All right, let's do one more problem. And this one we'll work through by hand. So let me jump over to just OneNote so it's a little bigger on your screen for you. And here we have a narrative, and this results in this probability distribution. So I don't expect everybody to, understand finance really well or anything like that for this course, but I'm just trying to show you some slightly more practical examples than things like rolling dice or flipping coins with silly betting games or something like that. So let's take a look at this example. We're considering an investment in a corporate bond. It pays a 6% annual yield. So really what that means is that we're giving a loan to a corporation, and they're paying us interest on that loan. They're paying us 6% of the amount that we loaned them each year. However, if you lend money to somebody, there's always a chance that they don't pay it back. The corporation goes bankrupt, runs into financial distress, whatever. We estimate there's a 5% chance that this company defaults on the bond within the next year. And in that case, I mean, this is, really complex what happens when a company goes into financial distress, but we just assume we lose our entire investment. Maybe maybe what the debt we're looking at is a type of debt that's not particularly, not particularly, as they would call it in finance, senior. Maybe it's not, one of the first debts that gets paid off. So we just assume we lose everything. That's probably a little bit too conservative for reality, but probably not all that far from the truth. And let's suppose that we also estimate there's a 10% chance that market rates drop over the next year, in which case, well, if let's say right now the going market rate is 6% for this type of debt, and a year from now the going market rate is 3% for this type of debt, well, people a year from now would rather have the bond that I have than issuing new debt to corporations than buying new bonds. They'd be willing to pay me extra. They'd be willing to pay me more for my bond than I paid for it. When the rates go down, bond prices go up because the bond that I'm holding was from a time when the rates were higher. It's paying a higher yield. So people would rather have it. They're willing to pay a premium for it. So we'll say that we think there's a 10% chance that the interest rates go down in the next year, the market rates, and that would mean we can sell our bond on the open market for an even bigger profit. For more than that 6% annual yield, we can sell it for a 20% profit. And we assume that in all other cases, if the company doesn't go into financial distress and the rate environment doesn't change significantly, we'll just hold the bond. We'll accept our coupon payment from the corporation, and we'll earn our 6% just as we kind of would expect from such an investment. So we have three scenarios, and here X is our return on our investment. It's our rate of return in year one. We have three scenarios. We can either get a plus 20% return in that favorable interest rate environment. That happens with probably 10%. We can lose all of our money, get a negative 100% return. That happens 5% of the time. And the rest of the time, we just collect our interest payment. We get our interest 6%. Now, we didn't say what the probability was of getting just our interest to 6%. We just said it was the rest of the time. But we do remember that for this to be a probability distribution, these probabilities have to sum to 1. I have 15 percentage points taken up between row 1 and row 3, the plus 20 and the minus 100%. Well, that means that I've got to have 85% in here, right? So the 85% plus 5% plus 10% gives me 100%. So I can solve for this number using the other two. Okay, so now let's, and down here I said compute the expected return and standard deviation of returns for the investment. So let's build off of our probability distribution here and compute an expected value. Remember that the expected value is the outcomes times their probabilities added together. So this next column, x times p of x, so plus 20% times 0.1. I'm going to think of x as having the unit of percent. I think that might be a good way to go about it. And then I'll think of percent as just a unit, as if it was like dollars or inches or feet or something like that, and just carry that unit through. So I'll do 20 times 0.1. 20 times 0.1 is 2. I'll do 6 times 0.85. Well, let me break out the calculator for that. My calculator is not cooperating, so we will break out Excel for that. 6 times 0.85 gives me 5.1. And then minus 100 times 0.05 is minus 5. So the expected return then is the sum of this column is plus 2.1. And remember, that's in units of percentage points. So my expected rate of return for this investment is 2.1%. That's taking into account that I get the 6% return most of the time. Occasionally, the company defaults on its debt and I lose all my money. And occasionally, the market shifts and I can sell my bond for a pretty good return for that year. Okay, then let's look at the standard deviation of returns. Remember, the first thing we got to do here is compute the variance. And for the variance, the first thing I got to do is find my outcome squared and then multiply by my probabilities, add together. So x squared, 20 squared is 400. 6 squared is 36. And 100 squared is 10,000. And x squared times probability of x. What is that? 2 times 400 is 800. Oh, that was the wrong column. This column times that column. 0.1 times 400 is 40. That looks better. 36 times 0.85. Let's see what that is. That is 30.6. And 0.05 times 10,000. Well, 0.05 times 100 is 5, and then times another 100 is 500. And the sum gives me the expected value of x squared. This is going to be 570.6. Let me just call it about 570. Now keep in mind, this is in like percent squareds, so it's kind of a strange number. So if I have these two, I can compute my variance. Well, I always forget that the writing doesn't kind of scroll with the text. I can compute my variance, expected value of x squared, or 570, minus the square of the mean, minus 2.1 squared. And that's going to be pretty close to 570. What's that, like 566 or something like that? Equals 570 minus 2.1 squared. Yeah, 565.59. And then my standard deviation is the square root of that. And let's figure out what that is. 23.8 or so. And now we're back in units of the original data in percents. So we just carried that percent through as if it was a unit. And I see that my expected return is plus 2% or so, with a standard deviation, something kind of like a risk of about 24%. It does kind of irk me when finance folks equate standard deviation to risk, because that's really not right, right? When we think of risk, we think of downside. Like if I walked up and just handed you a Powerball ticket, you wouldn't like throw it on the ground and run away and say, no, that's too risky. It's like, well, you didn't pay anything for it. So like you might win $500 million. It's going to have a very high standard deviation, your outcome there, but you're not like scared of that. That's not really risky. All the standard deviation is on the upside, right? All of the uncertainty is on the upside. Here, most of the uncertainty, most of the contribution to the variance in standard deviation is coming from the downside risk. So in this case, this 24%, this standard deviation is a little more representative of downside than upside. Do I really want to accept a coefficient of variation of like 10 times? Probably not. Do I want a volatility that's like 10 times my expected return? I could probably do a lot better than that just by putting my money in the S&P 500, right? Just by, you know, S&P 500 exchange traded fund shares, and you're probably going to get an expected value of like 7 or 8% ish, something like that, and a standard deviation of like 10-ish%. So probably not a great investment. I'd probably walk away from this one. It's a combination of the chance, my estimated chance of them defaulting on the debt being too high relative to the yield that they're paying. For me to be attracted to this debt, I would either require a higher yield, I'd require that this 6% be bigger so that this number ends up bigger, making my expected value bigger, giving me a better reward for the risk that I'm taking, or I'd require that this number be smaller, that the company be in kind of safer, in a safer financial status. Maybe have a little more cash reserves, a little less, say, total debt, be maybe in a stronger market position, something like that, so that my estimate of their likelihood of not being able to satisfy their financial obligations over the next year is lower. If this 5% went down to 2%, that would, number one, decrease the hit on the expected value, but number two, even bigger, it would substantially decrease the contribution to the variance. So if their chance of defaulting was a lot lower, was say half as much, my average return would be a lot better, and also my risk would be a lot lower. So either one of those, are what would be numbers we could play with. We could either say, well, if you want my money, get yourself in shape, in financial shape first, and then come and ask again when your 5% risk is down to like 2% risk of defaulting, or give me more compensation for taking on this big of a risk. So those would be the two levers we could play with, at least as far as we see here. Of course, in finance, there are, nearly infinite complexities that you could have. You could hedge out risks and do all kinds of interesting stuff. So, this is a naive point of view of managing an investment like this. So any questions on this example? Okay. But I think these two numbers would be enough for us to look at and say, walk away from this investment probably, unless we had a heck of a good argument for why we should stick with it. All right. So moving on then to some proofs of previous theorems. So I have this in a separate tab. Let me just close Excel for right now. All right. Okay, so we have a couple previous theorems that we had introduced in the past. And I want to just quickly go through some proofs. I'm not trying to make these all super formal, especially the discussion of the law of large numbers. Um, Chebyshev's should be pretty close to a real legitimate proof. Um, but I want to give two things. Number one, I want to give evidence for what I claimed. I claimed that these things were true, but you have no reason to believe that this is true. So let's give proof for it. Now that we've gone through chapter 4 and a bit of chapter 5, we have a bit more notation, and we can write these things a little bit more concisely. Um, and the other reason is just to get a little bit of appreciation of what's kind of under the hood of a lot of the stuff we'll be discussing, particularly as we move on to, say, chapters 6, 7, and 8. Every time that we say, here's a confidence interval, or here's a hypothesis test or something, there's something like this, there's an argument like these under the hood saying, yes, this is a legitimate thing to do. It's not like we're doing it because it feels nice, or it feels like it's the right thing to do, or even because somebody with a bunch of experience has done this a bunch of times and seen that it worked. We're really doing it on the basis of a bunch of mathematical formalism that says, yes, under these assumptions, under these types of models, this is a legitimate thing to do. Okay, so let's look at Chebyshev's theorem. Again, you can kind of transliterate his name in seemingly about 100 different ways, but that's how I chose to write it today, I suppose. So Chebyshev's theorem says that assume that the mean and standard deviation are finite, and that k is a number that's bigger than 0. Then the proportion of data points in a data set with a value more than k standard deviations away from the mean, I don't know why that's on a different line. The proportion of data points with value more than k standard deviations away from the mean is at most 1 over k squared. That's what Chebyshev said. Rewriting this in our kind of newer, fancier notation, this is really kind of what we mean, right? Is that the probability that a given data point, x sub I, is more than k standard deviations away from the mean. That means that the distance between xi and mu and the mean, which is the absolute value of xi minus mu, that's the distance between the data point's value and the mean, is more than, can I select this? There we go, is more than k standard deviations. So the probability that the distance between the data point's value and the mean is more than k standard deviations, or that's just another way of saying the probability that the data point is more than k standard deviations away from the mean. Chebyshev's theorem says that is what is less than or equal to 1 over k squared. We can use our complementary event rule, our data point being more than k standard deviations away from the mean. The complementary event is our data point is less than k standard deviations away from the mean. I'm not being super careful here with the strict inequalities when I'm verbalizing this, so I'm not super worried about the strict inequalities. Our data points, we can imagine as them being continuous, and so we don't have to really worry too much about that. So our complementary event to being more than k standard deviations away from the mean is being less than k standard deviations away from the mean. And the associated probability is 1 minus the probability of the complementary event. So 1 minus 1 over k squared. Okay, so let's look at the proof. We're going to assume that our data points are ordered according to their value. So x1 less than or equal to x2 and so on. We can split the data points then into 3 classes, say x1 through xj, that are at least k standard deviations below mu. So let's draw a little picture here to help us see what's happening. So going along here, I have, say, x1, x2, x3 up to xj. And then I have, say, xj plus 1 up to x xj plus m minus 1. And this is xj plus m up to xn. So I have these three classes, x1 to xj, xj plus 1 up to xj plus m minus 1, and xj plus m to xn. Now, somewhere in here, I also have a mean. Let's say it's here, and I have some standard deviation. And we're saying that x1 through xj are at least k standard deviations below the mean. So to the left of mu, if I go k sigma to the left of mu, to mu minus k sigma, the x1 through xj are the ones that are to the left of k standard deviations below the mean. They're at least k standard deviations below the mean. These are the ones that are really far to the left. Xj plus m to xn are at least k standard deviations above the mean. That's a k sigma there. So these ones are the ones that are at least k standard deviations above the mean in this third class here. And then I have ones in the middle, these blue ones, xj plus 1 up to xj plus m minus 1, that are within k standard deviations of the mean. The distance from any of these xi's in the blue to mu is less than k standard deviations. So these are within k standard deviations of the mean. So I have ones that are far to the left, ones that are far to the right, and ones that are kind of in the middle. Okay, so let's suppose we're talking about a population here. If we switch this to sample standard deviation and sample variance, uh, the uh, the same inequalities hold. It's just a little harder to, track all of the details through. But the same inequalities would hold there as well. So by definition, the population variance is the average squared deviation from the mean. We're going to take my xi, subtract mu, square it. We're back in chapter 3 now. Xi minus mu, square it. Add those together, divide by n. That gives me sigma squared. And I do that for all of my points, all of my data points, right? My variance touches every data point. If I exclude some data points, if I cut some data points out of this sum, if I only sum over the indices where the data points value is way off to the left or way off to the right, and I cut out all of these ones in the middle, I have fewer elements in the second sum than in the first sum, right? If anything, I've lost elements. I suppose maybe everything is kind of out at the edges, but if there's anything in the middle there, then I've gotten rid of some xi minus mu's that I had before. But these aren't just xi minus mu's, they're xi minus mu squareds. They're non-negatives. If I get rid of numbers that are non-negative from a sum, the value of that sum only can decrease. So here I'm summing over all of the data points in the data set. Here I'm summing over only some of them. So my value of my sum can only have gone down. But wait, if I'm summing over the indices 1 through j and j plus m through n, if I'm looking at the green ones and the red ones, those are all more than k standard deviations away from the mean. In other words, xi minus mu in absolute value is at least k sigma. They're more than k standard deviations away from the mean. But if we square both sides of this, we see that xi minus mu squared is bigger than or equal to k sigma all squared. So if I replace each of these xi minus mu squareds in the green and the red, where these are far away from the mean, if I replace it by basically, if I pretend that all of these green ones are here, and I pretend that all of the red ones are here, they only got closer to the mean. This will still have only decreased the sum. So if I replace xi minus mu squared with k sigma squared, either algebraically or kind of, more pictorially, we see that that sum can only have decreased. But wait, what do I have here now? I just have the sum of a constant, k sigma squared. This is only a constant. It's not dependent on the values of the actual xi's anymore. These terms up here were dependent on the value of the xi's. The xi minus mu was different for each term. But here it's not dependent on the xi's. So I just get one copy of k sigma squared for, the first one in the green, another copy of k sigma squared added on for the second xi in the green, and so on, and the same for the reds. Or this is really just k sigma squared, or k squared sigma squared, times the number of data points with value more than k standard deviations from the mean, times the number of data points that are in the green and the red combined. And then I still have my 1 over n kind of, that I'm carrying through the whole thing. But wait, if I combine these two together, the number of data points with value more than the k standard deviation from the mean divided by n, that sounds a lot like a probability. The number of data points that satisfy a certain event divided by the total number of data points, that's just a probability. That's just the probability that a randomly chosen data point satisfies that event. That's just the probability that a randomly chosen data point has a value that's more than k standard deviations from the mean. And what have we shown? We've shown that sigma squared is greater than or equal to, note that all of our inequalities point the same direction. That's very important. If I pointed one direction, if I kind of got smaller and then got bigger again, I'd have no idea what happened, but I got smaller and then smaller again. So sigma squared is bigger than or equal to k squared sigma squared times this probability. That's what I've summarized here. But then what can I do? I can divide through by k squared sigma squared. I know that sigma squared is strictly positive as long as my xi's are not all exactly the same. If even one of them is different from one other, my sigma squared is strictly positive and not zero. So, I mean, maybe we should really assume that there's at least two xi's that are not the same if we really wanted to be careful. This already felt like a lot, so I didn't throw that in there. We're also assuming that k is strictly positive, so k is non-zero. We can divide through by k squared, and we can divide through by sigma squared then. And the sigma squareds divide out, actually, nicely enough. And we get our Chebyshev result. Probability that the absolute value xi minus mu is bigger than or equal to k sigma, or the probability that a data point is more than k standard deviations away from the mean is less than or equal to 1 over k squared. That is our proof. We can do 2 lines, we can do a box, we can do a QED, whatever your favorite symbol is to conclude a proof in math. So I think we see that, these steps, none of the individual steps were super difficult to understand, but it is quite ingenious to come up with, with the thought of assembling these steps in this manner to get a result that's, that's meaningful and useful and, practical that we can use in other places. So it's not that any one of these steps was such a huge philosophical or logical leap, but it's the choices made along the way and the way that they were assembled. A lot of simple things got assembled in a very creative way to make a useful tool. Okay. A little bit like a bicycle, right? Like gears aren't super complicated and chains aren't super complicated, wheels aren't super complicated, but it takes some ingenuity and creativity to choose to put to choose to pick these components this way and put them together in this format. Okay, now let's go into something that's going to be a little more challenging for us, the proof of the law of large numbers. We have a couple issues here. One is that unfortunately there are several laws of large numbers. So, you know, I lied to you a little bit when I said this is the law of large numbers. That there are kind of several takes on the law of large numbers. But we're going to see, I hope we're going to uncover a little bit of the nuance and I would say even maybe a little bit of the beauty behind these arguments through this exposition. So this exposition of Chebyshev's theorem and its proof, it really is like a formal mathematical proof. I don't think anybody could poke holes in here aside from, me leaving off let's also assume that there are at least two outcomes that are different from one another, or two data points that are different, that have different values from each other. But this is going to be a little more kind of hand wavy. We're not going to dig into the details nearly as much for the proof of law of large numbers. Okay, so I have a few different, kind of points to make here, A, B, C, and D. So we're going to start off with a discussion of the weak law of large numbers. This is what the weak law of large numbers says. It says that x bar n, well, what is that? That's saying the sample mean for a sample of size n taken from this population. So I have some population, I take a sample of size n, we will assume it's with replacement, and I take that sample of size n and I compute the sample mean, I call that x bar n. If I take a sample of size 30, then I call it x bar 30. If I increase my sample size to 100, I would take that sample, compute its sample mean, I would call that x bar 100, and so on. And the claim is that as I take larger and larger samples, as n goes to infinity, as my sample size gets larger and larger, the sample mean sampled from this population with replacement. So I, take a person out, I write down their data value, I put them back, scramble the population up, pick another one, and so on. So I could pull the same person multiple times. That's why I can let n go to infinity for even a finite population. But the weak law of large numbers claims that the sample mean, the value of that approaches the population mean mu. So the larger and larger the sample, in some sense, the closer and closer our sample mean is to the population mean. That's the claim we're making here. Now, part B addresses maybe the elephant in the room. You say, hey, wait, that wasn't the law of large numbers we talked about in chapter 4. Yeah, this is a different law of large numbers. So, but it's intricately related to what we said in chapter 4. So we will get there. So we'll look at the weak law of large numbers that says the sample mean converges to the population mean as the sample size increases. Okay. Let's make some assumptions here. Let's assume that these individual draws from the population, x1, x2, and so on, are independent. So I'm making a random draw and I'm putting that individual back. I'm drawing with replacement so that I can have independent draws, and these draws are done independently. It's not like if I choose one, then that one's more or less likely to be chosen in the future. These are independent draws. So these would be kind of a standard random sampling from a large population. We'll also assume these are identically distributed random variables. So in other words, something like if I just do random sampling, everybody is equally likely to be chosen on the first round. Everybody's equally likely to be chosen in the second round also. The distribution stays the same from time to time. And we're also going to assume that we have a finite mean mu and a finite variance sigma squared. And we want to show the following. This is where the math gets a little more complex. There may be some of you who, have seen this kind of math before and appreciate it. And if you don't have a full appreciation of this, it's not a big deal. I want to show you a little bit under the hood, but this isn't going to be on the exam or something like that. So don't worry if you don't completely grasp this. But this is really what we want to show. We want to show that the distance between x bar n and mu, the deviation between x bar n and mu, how far apart they are, we want to show that that gets small. And instead of attacking that directly, instead of just saying that xn goes to mu directly, well, the way that we show that, what we mean by this statement here, what we mean is if we pick any positive number, we typically think of this as a small positive number. We pick some epsilon, some small positive number. Then we want to show that no matter how small that positive number is, whether it's 1 in 100 or 1 millionth or 1 billionth, we want to show that the probability that x bar n is more than that distance away from mu goes to 0 as n goes to infinity. So we're making a statement about the limit, but in terms of the probability of something being true. The probability that our sample mean is far away from the population mean goes to 0. So that's really what we're trying to say here. Okay, so if we take, say, a random variable x to be x bar n, right? If I took different samples of size n, if I take a sample of size 30, I write down that data set and I compute the mean, the sample mean, that's one possible sample mean. But if I took another sample, I'd probably get a different sample mean. So the sample mean itself is actually a random variable. Note that the mean of this random variable, the mean of x bar n, is actually mu. Let's argue that down here. What's the expected value of x bar n? Well, x bar n by definition is the sum of my draws from the population, x1 through xn, times 1 over n. So that's just what x bar n is. It's the x1 through xn added together divided by n. But remember that constants can come out of the expected values. We talked about that last time. 1 over n can come out in front of the expected value here. And then expected values can split sums apart. So expected value of x1 plus x2 through xn becomes expected value of x1 plus expected value of x2 all the way out through plus expected value of xn. But wait, each of these, the expected value of the first draw, that's just the mean of the population. If I randomly sample one person from the population, what's the expected value of that draw? That's just the mean of the population. The same for this one, all the way out to this one. So I just have n copies of mu added together with a factor 1 over n in front. 1 over n times n mu is mu. So we've shown that the expected value of the sample mean is actually the population mean. So on average, the sample mean ends up being the population mean on average. What about the variances? We also discussed briefly this property of variances. The variance of x bar n is again the variance of 1 over n times the sum x1 through xn. The 1 over n comes out in front of the variance as a 1 over n squared. That was a property of the variance. That's kind of related to how the variance ends up giving you the unit squared. It's kind of, you know, a similar idea. So we have 1 over n squared times the variance of the sum of the xi's. Since we assume these are independent draws, then we can split the variance of the sum into the sum of the variances as well. When we have independence, we can do this with variances. If we don't have independence, we can't do this. But the variance of a single draw is just sigma squared, and I just have n copies of that. So I have n sigma squared times 1 over n squared. We actually be a little careful here with the cancellation, not just sigma squared out the other end, but sigma squared over n. So the variance of the sample mean of for a sample of size n is actually sigma squared, the original population variance, divided by n. This over n here is quite important. As an aside, we'll see these two numbers, these two ideas pop up at the end of chapter 6 as well in the central limit theorem. So this will give us part of the proof of the central limit theorem, not the whole thing though. Okay, let's recall Chebyshev's theorem. So what did Chebyshev say? It said probability that the absolute value of xi minus mu, or here I'm taking my random variable to be x bar n. So the probability that the absolute value of x bar n minus mu is bigger than or equal to k standard deviations. K standard deviations of my random variable, the square root of the variance of x bar n, is going to be less than or equal to 1 over k squared. So just plugging in x equals x bar n into Chebyshev gives us this. But something that we notice here is this, and going all the way back up here, this thing that's really the thing that we're trying to work on, these look very similar. I have probability that the absolute value of x bar n minus mu bigger than or equal to something. I can say something about it, and I want to say something about it. Well, let's just equate k times sigma x bar to epsilon. We'll just pick that to be our epsilon. That's not a problem. Sigma x bar is just some number. It's, I guess, the square root of that number, right? So it's just some number, and we can choose k freely. So whatever epsilon you say or somebody else says that they want to use, they will want to use 1 in a million. Well, we just pick k to make k times sigma x bar 1 in a million. Or in other words, we just choose k equals epsilon over sigma x bar. So if epsilon is given and we want to find what k results in that epsilon, well, we just solve for k. But that means that 1 over k is sigma x bar over epsilon, or 1 over k squared is sigma x bar squared over epsilon squared. But wait, sigma x bar squared, I mean, that's just the variance of x bar. But that's just sigma squared over n. Okay, so 1 over k squared is just sigma squared over n epsilon squared. So what did we do here then? We have our probability by Chebyshev that absolute value of x bar n minus mu is bigger than or equal to, well, this thing, but we just equated that to epsilon, is bigger than or equal to epsilon. That quantity is less than or equal to what Chebyshev said, that's less than or equal to 1 over k squared. And 1 over k squared is just this thing, sigma squared over n epsilon squared. And clearly, as n goes to infinity, as n gets bigger, let me zoom in on this a little bit. As n gets bigger, the only thing that changes here, sigma squared, that's just the population standard deviation. That stays the same regardless of our sample size. And epsilon squared, well, epsilon was just the number we picked at the beginning. We said for a specific epsilon, do this, show that this thing is true, and do that for all epsilons we could pick. Well, the sigma squared and the epsilon squared are just constants. As n gets bigger, this factor on the bottom gets bigger. And if the denominator gets bigger and everything else stays the same, the fraction goes to 0. So we have proven, I think pretty carefully, that the weak law of large numbers is true. This is really the formal statement of the weak law of large numbers. This here. It's kind of hard to read, so to speak, so we often write it this way, that the sample mean goes to the population mean as the sample size goes to infinity, but written more specifically, more precisely, this is what we mean there. I guess there's one piece that we didn't really address, and that's this kind of all-important step here where I broke up the variance of the sum into the sum of the variances. We're going to address that a little bit later here. So there is still, I guess, a little bit of a hole in this proof, but I think this is a pretty solid proof. Okay, now a couple of notes to follow up on this. This is kind of cool that we did a proof, right? We did this formal proof of this thing, but you look at this and you say, wait, I mean, in chapter 4, we said the law of large numbers said something about the whole distribution. It said that like the frequency distribution, when we take a large sample, should look like the frequency distribution of the population. But this just says something about the mean. We've seemingly made a similar claim that the sample mean goes to the population mean, but about a much smaller thing. We're claiming that sample mean goes to population mean, but before we said that the sample frequency distribution approaches the population frequency distribution. That seems like a much, much larger claim. It actually turns out that this criterion gives us the whole frequency distribution. It just knowing that the mean goes to the mean is enough for us to conclude that the distribution goes to the distribution. And why is that? I'm speaking a little bit loosely here, but why is that? Well, so this bigger law of large numbers, so to speak, is sometimes called the Erdos law of large numbers, named after the mathematician Paul Erdos. That's probably a horrible mispronunciation of his name, so I apologize to him. Okay, so we only showed that the sample mean goes to the population mean. How can we link the sample mean going to the population mean to frequencies going to one another, or essentially probabilities of events going to one another? If the probability of any event under the sample approaches the probability of that event under the population, that would be enough, right? Because we could just make our events, we could look at event 1 being just outcome 1 and show that probability of outcome 1 in the sample goes to probability of outcome 1 in the population, and do that for each of our outcomes. This does get quite sticky and hairy if we try to move to a continuous distribution. So we're kind of sticking with our thought process being like discrete distributions, where these events consist of discrete outcomes. Okay, let's consider an event E. For each possible outcome, for each individual in the sample, or for each possible outcome, it's clearly true that either that outcome is in the event or it's not in the event. I think we'd agree there. So we have these xi's, these outcomes that we get from randomly drawing from the population. But associated with each of these outcomes is the determination of whether that outcome is in the event E or not in the event E. Let's make a new random variable. I draw an individual from the population. I look at that individual, that xi, And that's associated with a random variable yi that is 0 if the outcome that I got is not in the event, and it's 1 if the outcome is in the event. So yi is either 0 or 1, indicating whether or not the outcome is in the event that we're considering. Well, then the number, so we drew a bunch of these, we drew a bunch of draws from our population to make a sample. We have x1 through xn. The number of xi's, the number of sample data points that are in the event, is the sum of the yi's. For each of the xi's that's not in the event, the yi would be 0, it just doesn't contribute anything. And for each of the xi's that is in the event, the yi will be 1, and we'll tick one more onto that number in the event. So the number of xi's in the event is the sum y1 through yn. But wait, the probability of the event under the sample then is just the number of outcomes in the event over the total number of trials, or that's the sum of the y's divided by n. Well, that looks a heck of a lot like just the average of y bar. But wait, so y bar goes to the true mean of the true mean y as the sample size increases, which, well, that's just the true probability, the population probability of the event, right? I've constructed a new random variable where the probability of the event is the average of that random variable, the sample mean of that random variable. And by the weak law of large numbers, sample means converge to population means. So this sample mean of y converges to the population mean of y, which is just the population probability of the event. And again, if we consider our individual events, if we take event 1 to be just outcome 1, then the probability of outcome 1 from the sample side approaches the probability of outcome 1, the population probability. And the same for outcome 2, and the same for all of our outcomes. So we do get the full frequency distribution, the full sample frequency distribution approaching the full population frequency distribution, actually from just this weak law of large numbers, just the statement about the means. Okay, so that was one bit that needed cleaned up. We have another bit that needs cleaned up, and this is fairly technical. I'll probably just hit the high points here. But one important note on the variance of x bar n. Again, I said by independence here. Oops, by independence, definitely don't want to cross it out. By independence, I said that we could break up the variance of the sum as the sum of the variances. I gave no reason why that ought to be true. That's what we're going to explain now. Is it true that the variance of the sum of two random variables is the sum of the variances of those random variables if those two variables are independent? The answer is yes, and this is the argument in support of that. We're only going to look at two random variables, but this would, of course, generalize, right? If we had x1 through xn, we can consider x1 through xn added together. We can consider x1 plus x2 through xn added together, break the x1 off, and then break the x2 off, and then break the x3 off, and so on. So we're just going to look at two random variables, and we can prove the whole thing without loss of generality this way. Okay, so what is the variance of x plus y? The variance of this random variable is the expected value of that random variable minus the mean of that random variable all squared. So I have x plus y minus expected value of x plus y, that whole thing squared, all inside of another expected value. kind of a little bit complicated to write it this way. There's lots of parentheses and a couple expected values, but if we work from the inside out, it makes a little more sense. Okay, so what could I do here? Well, inside of this squared, if I look at all of this stuff, I know that regardless of independence, I've already proven that expected value of x plus y is expected value of x plus expected value of y. Now this has a minus in front of it, so the minus distributes to both of them. And I can rearrange. I can group this x with this minus expected value of x, and then the same with y minus expected value of y. So I have expected value of x minus expected value of x, which I'm going to now write more conveniently as just mu x, plus y minus expected value of y, or y minus mu y. That is all squared. And then we take the expected value. But if I multiply this out, let me actually erase these little arrows. I have a first term, x minus mu x, a second term, y minus mu y. Those are added together and squared. If I multiply this out, I get the first term squared plus the second term squared. And then I have a cross term. I have a plus 2 x minus mu x times y minus mu y. I need to make sure that when I multiply these out, I don't forget about that cross term. I have kind of an a plus b all squared. That's a squared plus b squared plus 2ab. And then, of course, all of this is inside of the expected value, but the expected value can just break the sums apart. So for this next line, I have expected value of x minus mu x all squared. That's this bit. Plus expected value of y minus mu y all squared. That's this bit. Plus 2 expected value of x minus mu x, y minus mu y. This is the bit that is unfortunate. Something important to note is that the expected value of the product is not the product of the expected values. The expected values split sums and differences apart, but not products or quotients. We note, though, that expected value of x minus mu x all squared, well, that's just the definition of variance of x. Expected value of y minus mu y all squared, that's the definition of variance of y. But importantly, we end up with this vestigial stuff at the end. It seems like we've made a serious misstep, right? We've claimed the variance of the sum is the sum of the variances, but it looks like the variance of the sum is the sum of the variances plus some other stuff. Now, this is the magic of independence. Let me give myself one more line here. The magic of independence is that this extra stuff ends up being 0 if we're independent. If we're not independent, things are much messier. If I'm dealing with variables that have some dependence between them, where they're dependent variables, much, much messier. If we get to assume independence, things are so much cleaner. So claim this expected value is 0. Let's look at what this expected value is. Again, I multiply out this binomial. My first give me x times y, so I have an expected value of x times y. My outsides give me x times negative mu y, that's a minus expected value of x times mu y. Mu y is just a constant, it just comes out of the expected value. My inners give me minus mu x times y inside the expected value. And again, the minus and the mu x just come out of the expected value, leave me with expected value of y. And then I have plus my lasts, expected value of negative mu x, negative mu y. That's just expected value of mu x times mu y, but that's expected value of a constant. That's just that constant, minus mu x, mu y. Oh, this minus mu x, mu y. I actually see here that this expected value of x is just mu x. This expected value of y is just mu y. So I have expected value of xy. Let me give that a different symbol. Minus mu x mu y minus another mu x mu y plus a mu x mu y. So say these guys cancel. And then I have minus mu x mu y. Okay, so all of this extra stuff, the stuff turns out to be expected value of xy minus mu x mu y. What is expected value of xy? By definition, this is x1 times y1, say the first outcome for x times the first outcome for y, times the probability of that. The probability that x equals the first outcome, x1, and y equals y1. Or we could have x's second outcome and y's first outcome, that's another possibility, times the probability that x equals x2 and y equals y1. Out through xn times y1, we have x's nth outcome and y's first outcome, xn times y1 for the outcome, times the probability of that outcome, probability of xn and y1. Or coming back here, we could increment y. So these were all of the different x outcomes associated with the first y outcome. This is all of the different x outcomes associated with the second y outcome. And so on, all the way down to all of the, oops, I lost a, there we go. All the way down to all of the x outcomes associated with the mth y outcome. So we've gone through all of the pairings of x's different outcomes and y's different outcomes, their products multiplied by their probabilities. And here's the magic. Using independence, all of these probabilities that have an and here, probability x equals x1 and y equals y1, get to break up into the product of two simpler probabilities, one with just x, one with just y. Probability x equals x1 and y equals y1, since x and y are independent by assumption, that's the probability x equals x1 times probability y equals y1. And so on down the line. And it turns out now we can factor out from the first line here, we can factor out a factor of y1 times probability y equals y1. If we factor out y1 times probability of y1, this is what we're left with. x1, probability of x1, plus x2, probability of x2, and so on. We can do something similar in line 2, all the way down the line. And we notice that in brackets here, x1, probability of x1, summed up through xn, probability of xn, is just the expected value of x. That same expected value of x occurs in line 2, and every line down through line m. But wait, this is just y1 probability of y1 times expected value of x plus y2 times probability of y2 times expected value of x, and so on. Everything has an expected value of x factor now. That can factor out, and I get y1 probability of y1 plus y2 probability of y2, so on, times expected value of x, but that's just the expected value of y. Or in other words, I just end up with expected value of y times expected value of x. Oops, I don't know what happened there. Love Control Z. That's expected value of y times expected value of x, or mu x mu y. So we have shown under independence, that was crucial for us to be able to break up these complicated probabilities into simpler ones and do all of our factoring. Under independence, expected value of xy equals mu x mu y. Or in other words, the difference between them is indeed 0. So we have now shown that the variance of the sum is the sum of the variances if we have independence. So now we've kind of, I think, filled in that hole in the weak law of large numbers. And in the last few minutes here, there is one last detail that I want to discuss. And just kind of an interesting little example. Oops, I entered too many times and now I have I moved my text and not my picture. Let me just slide this picture down a little bit. All right, let's see. Is this gonna good? All right. Okay, so one last little thought on this. So we might look back up here and we say, well, if there's a weak law of large numbers, it kind of suggests that there's a strong law of large numbers as well, right? This weak law of large numbers says that the sample mean goes to the population mean as the sample size increases. What does the strong law of large numbers say? It actually says the same thing. It actually says the sample mean goes to the population mean as sample size increases. But this type of convergence is different. This little detail here, exactly what we mean by that is different. So this actually is kind of an ambiguous statement. Sometimes we say it this way. So there are different types of convergence in probability and statistics. And here's an example to illustrate the point. Let's consider these two probability distributions. Probability distribution 1 over here comes up 0. It has outcome 0 with probability 1 minus 1 over n, and outcome n with probability 1 over n. What's its mean? Well, its mean is 0 times 1 minus 1 over n, that's 0, plus n times 1 over n, that's n times 1 over n, or that's just 0 plus 1 or 1. The mean of this is always 1. If I pick n to be a small number or a medium number or a big number, the mean is always 1. Because it's less likely to get a bigger outcome. So the less likelihood and the bigger outcome perfectly balance out. If I let n go to infinity, this distribution, I have an outcome that's further and further out to the right, but its probability goes to 0. So in the limit, its probability of that thing that's far out to the right is 0. I have all of my probability concentrated at the outcome 0. This distribution, this limiting distribution, has a mean of 0 pretty clearly, right? I have outcome 0 with probability 1. 0 happens all the time. The mean is 0. But wait, that means that this distribution approaches that one as n goes to infinity. But when, say, n is 1, the mean is 1. When n is 2, the mean is 1. When n is 3, the mean is 1. When n is 4, the mean is 1. But somehow in the limit as n goes to infinity, the mean has to end up being 0. There's this discrepancy there. So there are ideas of things like convergence in distribution versus convergence in probability versus things like convergence in the mean or convergence almost surely. There are different modes of convergence. The central limit theorem we'll see in chapter 6 uses the idea of convergence in the distribution. It's a somewhat weak version of convergence. So again, I'm thinking of a lot of this, particularly from particularly from maybe like here on, as being more expository and just showing you some interesting things, but hopefully you were able to follow Chebyshev, and ideally you were able to follow kind of the general thrust of this argument with the law of large numbers, parts A and B here. You know, if a couple of details escaped you, that's fine, but hopefully you were able to follow kind of the general ideas here, and you know, hopefully this showed a little bit of evidence that these important theorems are actually true. we saw that the law of large numbers proof relied directly on Chebyshev. So even though maybe Chebyshev isn't so useful in practice, maybe something like the empirical normal rule is a little more useful in practice. Chebyshev is super important to underlie these proofs because remember, Chebyshev works all the time, where the empirical normal rule only works under the assumption that we have an approximately normal underlying distribution. Yeah, so hopefully that firmed up a little bit of some of the stuff that some of the loose ends that we hadn't tied up. And you can see that, definitely having this language of probability and so on was super helpful to be able to prove Chebyshev, and having experienced things like expected values and so on was super important to understand these proofs of the law of large numbers. So jumping back to our other note here. So we didn't get to binomial distribution. That's okay. We'll bump binomial and Poisson to a supplemental video, 5.2 and 5.3. I'll probably post that probably right after class, and then shoot out a Blackboard announcement about that. So any questions before we break for today?